Good morning, students. In the previous class, we were discussing this particular exercise of class A operation of the power amplifier for the emitter follower circuit. So, just a recap, just for you to see this particular circuit which we have been discussing in the last class. We have a 50 ohms and 100 ohms resistors here as R1 and R2. And we have an emitter resistor here as 16 ohms and the load resistor here as 16 ohms. Then the collector is directly connected to the power supply and supply voltage is 12 volts. Now using these values, we will have to determine the DC and AC load line endpoints and we have to find out the maximum peak to peak output voltage for the circuit. We had already proceeded with the DC load line computation in the last class itself, and let me show you that. The DC load line was found out this way. The voltage at the base is given as 100 into 12 by 50 plus 100 because we have two resistors there totally, and it is across 100 ohms there. 12 is the VCC, so we get 8 volts. Going for the approximate analysis of the circuit. Now, quiescent current, collector current is nothing but emitter current. That is 8 volts is VBB minus VBE divided by 16 ohms at the emitter, that is 456 milliamps. So, when we find out the quiescent current, the quiescent voltage between collector and emitter is 12 volts minus IC into RE or IE into RE. VCC minus IE RE. We get around 4.7 volts. IC sat is 12 volts divided by 16 ohms, the emitter resistor, so we get 750 milliampere. And VC cutoff is, as we already know, it is equal to VCC equals 12 volts. So we got the DC load line, we got the quiescent point also. Now proceeding with the AC load line, we have the small Re is 16 parallel with 16, the dynamic resistance at the emitter. Don't get confused with this small Re as the Re model, not that way. We use the small Re for the purpose of modeling in terms of AC analysis in module 1. But here in module 5, when the same symbol is utilized, it is not that particular Re. It is the dynamic resistance at the emitter, which is capital Re parallel with capital RL. That is 16 ohms parallel with 16 ohms. That is 8 ohms. Please remember this. This is not our small Re which we discussed in module 1. Just like we had beta also in module 1, that was IC by IB. But when we discussed the feedback point in module 3 and in module 4, not exactly in module 3, in module 4 when we discussed feedback, that beta was actually the feedback factor, it was not the gain of the transistor that way. So we use similar symbols at many places, but the symbols will have meanings with reference to the context at that particular discussion. So that way the small Re is the dynamic resistance at the emitter. Why do I say dynamic? Because with respect to AC we are finding out. So that is capital Re in parallel with capital RL, that is 8 ohms. Now we already have the formula for IC sat in the AC analysis. Let me show you that again. Just for a recap, we have this IC sat. ICQ plus VCQ divided by small rc, and VCE cutoff is VCQ plus ICQ into small rc. In the case of emitter follower, instead of small rc, we are using small re. That's all. So otherwise, we have found out the quiescent DC current. We have found out the quiescent DC collector to emitter voltage as well. Now using them and using the small re, which is across the emitter, we are going to find out the AC load line points for the emitter follower. That is this calculation now. IC sat is ICQ 0.456 plus VCEQ divided by RE. VCEQ is 4.7 volts divided by RE is 8 ohms. So that way we get 1.04 amperes. Now you can see the difference here. IC sat in the DC load line is 750 milliampere, whereas in the case of AC load line it is 1.04 amperes. This we have seen earlier also. The saturation current in case of AC load line is larger than that of DC load line, and naturally the cutoff voltage at the AC load line is lesser than that of DC load line. That also we will see now. VCE cutoff is 4.7 plus 0.456 into 8. VCEQ plus ICQ into RE. That you get around 4.7 plus 3.65 is 8.35 volts. You can see 8.35 volts is less than 12 volts here. Now to find out the maximum peak to peak voltage. Here maximum peak voltage is 6.65. You can see here. ICQ into RE. You can see ICQ is 450 milliamperes. RE is 8 ohms. So 0.456 into 8 is 3.65 volts. So that is the maximum peak voltage. That is where the AC load line has an end point, right? So maximum peak to peak voltage is 2 into 3.65 is around 7.3 volts. You can look at this. Even though we have supply voltage from 0 to 12 volts, the faithful peak to peak voltage which we get from this power amplifier is only 7.3 volts. If at all the output voltage exceeds 7.3 volts, then we will have a clipping and we will have unfaithful amplification. So let us proceed with this class A operation. At the right side you can see class A means complete 360-degree cycle is available at the output. Class B means only 180 degree. Class AB means in between 180 and 360. Class C means less than 180. You can see that in the diagram at the right side where it is beautifully indicated. So now using this class A operation, we have to have full cycle of the input at the output. You can see at the bottom you are seeing the circuit diagram where we are using again a voltage divider bias network for amplification, and input signal is 360 degree here, even output signal is 360 degree here with 180 degree phase shift here. As you already know, the common emitter amplifier provides 180 degree phase shift. So you can see the complete input signal is reproduced at the output and there is no clipping there. It is a faithful amplification. For finding out the range of faithful amplification only, we go for the concept of AC load line. So now let us proceed with the class A operation. Till now we have plotted the DC load line and AC load line for class A operation. Now finally we are dealing with power amplifiers. Now in the case of power amplifiers, we want to find out the efficiency of the amplifiers, because in case of power amplifiers, as the current is in amperes, voltage is in volts, the power will be in watts. Unlike the small signal amplifiers where our power consumption used to be in milliwatts, in many cases we could ignore that. But in the case of power amplifiers, it will be in watts or sometimes in kilowatts also. If it is for high power audio applications such as musical concerts or public gatherings, public speeches, in such case, the audio amplifier will be pumping out lot of power through the loudspeakers. So at times the power can be kilowatts also in case of audio power amplifiers. Now we want to find out the efficiency. So let us find out the power gain. Power gain is P out by P in into 100%. That is the gain. Now what is P out here? P out is AC output here. What is P in here? P in is not the input signal's power. Please understand. P in is not the input signal's power. Is it so or is it not so? Just look at the screen and tell me. Are we considering the input signal's power or not? Okay, no one is telling me. Let me only tell. Now here, input power is also equally strong. Unlike the small signal amplifier, input power is also equally strong. And output power is supposed to be much more stronger as far as power is concerned. And we are supplying a DC power also here. That VCC and ICQ is basically the DC power, right? ICQ is the quiescent current that is flowing through the circuit, and we are giving this VCC. So when the transistor is operating in the quiescent conditions, across the whole circuit there is VCC, and across the collector there is ICQ flowing. So there is a DC power going. That also can be considered for our power analysis, because that power is also not going to be negligible. As you see in the previous examples, when the current is around 0.5 amperes, we had around 456 milliamperes in the previous exercise, if I remember correctly. Let me see. Yeah, it is 456 milliamperes and VCC is 12 volts. So we can say transistor is dissipating a DC power of 456 milliampere into 4.7 volts. Across the transistor itself, this ICQ and VCUQ is there. So how much is this 0.45 into 4.7? Approximately, if I say it as 0.5 into 5. 0.5, let us say I consider this ICQ is as 0.5, just for the sake of our idea of the power rating of the transistor. Let me consider this as 0.5 amperes. And let me consider this as 5 volts. So across the transistor you can see 0.5 ampere into 5 volts. V into I is P, right? So it is 0.5 into 5 is 2.5 watts, which means the transistor is dissipating a power of 2.5 watts. Now, if we want to have a safe operation of the transistor, we should actually have the rating of the transistor double of this value. So, when this is equivalent to 2.5 watts, 0.5 ampere into 5 volts is 2.5 watts. Now, naturally, we should have a transistor which will bear at least 5 watts of power. Now that is the idea. I am just talking about transistor itself. Transistor is dissipating 2.5 watts of power now. That means transistor should have at least the maximum rating of 5 watts. In that case, transistor will be handling half of its load as the maximum capacity, and the life of the transistor will be more. Otherwise, if at all we choose the transistor having 2.5 watts power only, the transistor will not withstand its life as such. It may fail earlier. So this is how we decide the power rating of the devices now. Now coming back to the circuit diagram. Now in this class A operation, when there is this IDC and there is VCC, we can ignore the power consumption at the base for that matter. If we consider only the power at the transistor now, transistor's collector and emitter, you can see there is this 0.5 ampere going down, and the total circuit is given the voltage of 12 volts. So 12 volts into 0.5, because there will be power dissipation across this resistors also, right? Across the collector resistors also, across the emitter resistors also. P equals I squared into R, or P is equal to V squared divided by R. So there is power consumption across the, or power dissipation I should say, power dissipation across these resistors also. So that way, if we consider the previous example, 0.5 ampere into 12 volts is around 6 watts of power. The whole circuit is consuming 6 watts of power always. Now, should we consider that or should we not consider? That was my question. For the timing, let us not consider that, because that power is for the working of the circuit itself. Now, let us see the input power as well as the output power. Now, you can see P out is V RMS square divided by RL, the output AC power divided by the load resistor. V RMS squared. What is RMS? Root mean square. RMS is nothing but VP divided by root 2, right? Or VPP divided by 2 root 2, right? I hope you remember those formulae. Let me write it. Let me change the color. V RMS is equal to peak voltage by root 2, right? Or peak to peak voltage, or peak to peak voltage divided by 2 root 2. This formula you already know. Now, Vrms squared by RL, power output is equal to V square by R, right? P is equal to V into I is equal to V by R. So, P is equal to V square by R. So, at the output, as you know, the RMS value is nothing but the equivalent value of the DC at the output. In general, when we take average of AC wave, average upper one is plus, lower one is minus. So, if you take average value, it is going to be 0, right? For any AC signal, the average voltage is going to be 0. But AC also has a equal effect as the DC, right? When AC passes through an electric bulb, the bulb glows. Inside the bulb, let us say there is an incandescent bulb. Inside the bulb, there is a filament, tungsten filament. Tungsten filament is a resistor there. So, through the resistor, when AC is moving, the resistor is heating up and it is producing heat and light together in the case of an incandescent lamp. So, AC is also producing the same effect as DC. For example, in an electric heating coil, when you apply AC also, the coil is going to be heated up because the coil is nothing but a resistive element there. Even if you apply DC also, it will heat in the same way. But the point is, we are using AC for our regular domestic and industrial applications as the power source or the signal of power. But otherwise, AC and DC will have the similar effects. For that purpose only, we go for RMS value to have a comparison with the respective DC counterpart. That is why root everywhere in this, let me change the color. Or let me change it later on because I am using this red color only. You can see here, everywhere in this wave, somewhere some samples are taken. In this AC wave, samples are taken and they are squared and their square root is taken. Why they are squared? Because we have negative cycle also. Their square is taken because squaring is done, then the root is done. That is what is called root mean square. Then the mean is taken of all the samples. Then we will get the RMS value, which means when we say 220 volts is the RMS value of a regular AC signal, actually the 220 volts is RMS value in the sense its peak value can be much larger. You can calculate later on. When we say 220 volts is the RMS value for AC signal, its peak value can be 314 volts and peak to peak value can be 628 volts. That means the regular AC voltage which we are using at our home or in the office or anywhere, even though we say 220 volts, it is around 630 volts peak to peak value. One peak is around 350 nodes because it is a continuously changing wave. You can see here, it is a continuously changing wave. Whereas we equate it to DC because we know that it will have the same effect as the DC when we apply it to resistive load. That is the purpose of finding out the RMS value. Square it, no, sorry, take samples, square it, then take a mean, take a root. It is in the reverse order there. Square, mean, root. But we call it as root, mean, square, RMS. They have been writing it from the beginning like this and we have been telling it like that. Otherwise it is VSMR. First square it, take the samples, then square it, then take the mean of the squares, then take the root. You should square because you are having a negative cycle also. So take some samples there, different samples at different places. Then after squaring all the values of the instantaneous values of the samples, take a mean of that and take the root of the mean. That will be equivalent to the effective DC value corresponding to the same AC signal. Otherwise, as I told you earlier, we cannot take the average of AC signal because average of AC signal is always 0. That is the reason we have this VRMS now. So output is VRMS square divided by RL, but VRMS is VP by root 2 is equivalent to VPP by 2 root 2. Now when you square it here, VPP by 2 root 2 whole squared is what? VPP is in this case what? V out itself. So V out squared, 2 root 2 squared becomes 8. Root 2 squared is 2 and 2 squared is 4, 4 into 2, 8. That way VRMS square divided by RL is V out square divided by 8 RL. That is nothing but maximum peak to peak voltage at the output squared divided by 8 RL. V out is what actually in our case? We can consider for our case, we can consider the maximum peak to peak output which is possible through the load line. We have seen already the AC load line. So instead of V out, we can directly write MPP, maximum peak to peak value, whole squared divided by 8 RL. This is the output power in the case of faithful amplification. Now coming to the input power is nothing but V in squared divided by 8 into Z in. Again, P in is again V in square divided by the load there, right? V in square divided by 8. Why? Again, at the input also we have to take the RMS. Input is also AC wave, right? So ultimately it becomes V in square divided by 8. Because we did not worry about RMS condition at the input. At the input also RMS has to be considered. That way it is V in square divided by 8 in and divided by Z in. That Z in is the input impedance of the amplifier. Now using this, we can find out the power gain, that is P out by P in. Later on we will see how to find out efficiency of the circuit also. Now this is the power gain. Now let us see about the efficiency. That is when I told you, should we consider the DC power or not? Now for calculating efficiency, we are considering the DC power. You can see here, efficiency eta is equal to AC power by DC power. Our output is AC power, but the circuit is working in DC conditions. So now efficiency is PAC by PDC. PAC is what? V out square divided by 8 RL. That is nothing but the output power. We need not worry about the input power now. But the DC power is what? DC power is VCC into IDC, as I mentioned you earlier. Even in the absence of the signal also, the amplifier is going to draw power. To quote the previous example now, the amplifier was having around 0.5 amperes of quiescent current there and the supply voltage was 12 volts. So 12 into 0.5 is 6 watts. Even in the absence of the input signal also, 6 watts power is going to be consumed by the circuit. For example, let us say as soon as the power amplifier is turned on for a public function or for a musical concert, let us say singer is not yet singing by taking the mic set, or the speaker is not yet speaking. Even then, amplifier is turned on and the amplifier is drawing power continuously, even during the absence of the input signal as well. That's why I have been calling this as a static power consumption of the circuit. Static power basically means that circuit keeps consuming electric power even in the absence of input signal. Dynamic power consumption means the circuit is going to consume power when the input signal is present. That is called dynamic power consumption. Now in this case, we are considering the static power consumption of the transistor for calculating efficiency as such. So efficiency is PAC by PDC. PAC is V square by 8RL. PDC is VCC into IDC. Now please understand, power gain is different, efficiency is different. Power gain is output power by input power. Efficiency is AC power by DC power in the case of power amplifiers. Let me proceed. Let us have one more exercise. Look at this boy who is trying to lift a weight. Now this is a bigger exercise. In the previous slides I showed you some other funny pictures of exercises. Here you can see the boy is putting a hard effort to lift the load because it is now a power exercise, right? We are dealing with the power amplifiers, efficiency and power gain. So now this exercise is a power exercise. So I thought, let me put a picture for you to just to have a paradigm shift or just to have a humor or fun in between the learning process. Now there is another exercise. You can see here the lady is thinking, sitting on the treadmill machine, the lady is thinking, should she go for the treadmill machine's exercise or not? Now you can admire the boy who is trying to lift the load, but at the same time you can pity the lady at the right side. She is yet to decide whether she wants to go for this high power exercise or not. Okay. Now leaving the funny part, let me go to show you the exercise. We have to take up this solution of the exercise now. So we are like the boy at the left side. We are going to put our effort. We are not going to think about whether we want to solve the exercise or not. Whoever is active in this class with me, okay, there are 26 students with me. At least with these 26 students, I think all of you are ready to have this exercise, like the boy at the left side, unlike the lady at the right side. So let me show you an exercise now. Exercise 3 with the power amplifiers. Find out the transistor power dissipation, power gain and efficiency for the circuit given in exercise 1. If the input voltage is 200 millivolts peak to peak and output voltage is 18 volts peak to peak and the input impedance of the base is 100 ohms. Can my students note down these values and can you tell me the answer? Later on only I will show you the answer. I have already given you enough tips about how to find out transistor power dissipation, how to find out power gain, how to find out efficiency. Now, I am telling you the circuit given in exercise 1. I am going to show you that circuit given in exercise 1 also. But you have to note down these values. 200 millivolts peak to peak is the input voltage. 18 volts peak to peak is the output voltage. And the input impedance of the base is 100 ohms. Are my students noting down? I just want to know whether you are noting down or not. Either you unmute and tell me or you put it in the chat box. If you note down, then I will go to the previous slide where I have shown you exercise 1. Are you people noting down? Nobody is telling yes also. Okay. 3 students have told okay and yes. Fine. That is enough. Now remember these values. Input voltage is 200 millivolts peak to peak. Output voltage is 18 volts peak to peak. Input impedance of the base is 100 ohms. Let me go to the previous slide where I will show you the formula. power gain is Vrms square divided by RL, that is V out square divided by 8RL. P out. P in is V in square 8 Z in. You know the value of the Z in now. Z in is 100 ohms and output voltage is 18 volts. Input voltage is 200 millivolts. So you have this. Input voltage is 200 millivolts. Output voltage is 18 volts. You have Z in. Okay. 100 ohms. Now let me go to the slide where I have exercise 1. Now this is that exercise 1. Right. In this exercise 1, VCC was 30 volts. Now what we want here, we want ICQ, right? ICQ we have already found out, right? ICQ is 148 milliampere, or we can say 0.148 amperes. Now when we know this 0.148 amperes, that is enough, right? For our calculation, it is enough. So let us proceed now. We have this V out now, and we have this V in now, we have this Z in now, we have that IDC now, right? IDC is ICQ itself, 148 milliampere. We have the VCC, VCC was 30 volts. What we want is RL now, right? RL we want. What was the RL there in exercise 1? RL was 180 ohms. So note down ICQ 148 milliampere, RL 180 ohms, VCC 30 volts. VCC 30 volts, RL 180 ohms. Is it so? RL, is it 180 ohms, or is RL parallel with 120 ohms? As far as AC is concerned, 180 ohms and 120 ohms are in parallel, right? As far as AC analysis is concerned. So then remember this exercise, VCC 30 volts, RL 180, RC 120, and we have found out ICQ, that is 148 milliampere. Okay, and we have proceeded the AC load line here. Now coming back to that exercise, remember the formulae. P out is V out square by 8RL, P in is V in square by 8Z in, and efficiency is PDC, PAC by PDC. Now I want you to tell me the answer by solving this exercise. I'll be waiting for some time. For the time being, don't consider that RC now. Let us consider only RL, because RC is part of DC power also. If at all we want to have very accurate analysis, then we have to go for considering RC also. But in this case now, don't consider RC, consider only RL. Okay, Sayan has given the answer, power gain as 64.8%. Let us see. You will not get 64.8% here, because I showed you a tabular column earlier where class A power amplifier efficiency is much lesser. You will not get 64.8%. Check your calculations once again. Anyhow, later on I am going to show you the answer. As I told you, don't consider RC now, consider only RL. What about the other two students? Three students told me, yes sir, for noting down the values. Only Sayan has given the answer now. Okay, Lokesh is giving the answer. Power gain is 45%. Let us see whether it is 45%. Actually, it will be still less. Typically, class A power amplifiers gain will be somewhere between 25%. Still, up to 50% is also possible based on the circuit design. Okay, two students have given the answer now. Let us see the answer. Rohit has given the answer as power gain is 45%. Let us see the answer now. So the transistor's power dissipation is 9.28 into 0.148. 9.28 volts was VCEQ and 0.148 ampere was ICQ. So the transistor's power dissipation is 1.37 watt. Approximately, if we take it as 1.5 watt, the transistor must have the maximum power rating here as at least 3 watts for a safe operation. So this is transistor power dissipation. Next one, output power is 18 square divided by 18 to 180. Here I have considered only RL. Actually, in the formula also only RL is mentioned. So V out square divided by 18 to RL, as RC is part of the DC power also. That is why let us consider only RL. 18 square divided by 8 RL, that is 225 milliwatt. This is the output power. Input power is 0.2 square divided by 8 into 490 parallel with 68 parallel with 100. Why this is so? Because there is the R1 and R2 also, right? In that circuit, there is R1 and R2 also. Even though the input impedance of the base is 100 ohms, it is given here input impedance of base is 100 ohms. It is not given that R1 and R2 can be ignored because we are dealing with power amplifiers. So then we have to consider the input side circuitry also, as we had done it in the AC analysis. So that way, we have that R1 and R2. R1 and R2 and parallel with the Zin. That is the total input impedance of the circuit. In the problem, it is given input impedance of the base only, not as the complete circuit. Please remember, students have to be careful when you read the terms here. You can see here, input impedance of the base. Just like we had this beta into RE in our first module. Same way. So he does not say that the total input impedance of the circuit or the amplifier. He is not saying that. He is saying input impedance of the base. That is where you have to be careful. Of course, I did not spend much time there showing you the circuit diagram there of exercise 1. But now I am telling you that the R1 and R2 also have to be considered now, because they are part of AC analysis. So that is total Zin now. 490 parallel with 68 parallel with 100. So 0.2 squared, V in square divided by 8 into Zin, we get around 0.134 milliwatt. Now when we get this 0.134 milliwatt, the power gain here is 225 divided by 0.134, that is 1679. 225 divided by 0.134, 1679, approximately 1700 times is the power gain. That means the power gain of this amplifier is really very good. Output power by input power is really very good, we can say. What about efficiency? Let us see that now. Now IB, the base current is 30 divided by 490 plus 68, that is 53.76 milliampere. Why are you considering IB again? Let us see now. This is total 30 volts and 490 plus 68, that is the current that is flowing through that resistive network, that is 53.76 milliampere. So IDC, we have to consider this IB also now. Earlier I mentioned that ICQ is sufficient at that time for a rough estimate of the DC power. But we have to be more accurate here, because even with those resistors, there is the current flowing. Even though I call it as IB, actually it is the current going through R1 and R2, that is 490 and 68, they are connected across 30 volts. So maybe in the slide I'll have to change it now. Instead of IB, let me change it as current through that R1 and R2, or IR1 is equal to IR2, ignoring IB for that matter. So this is now 30 divided by 490 plus 68, 53.76 milliampere. Totally the DC current consumed by the circuit is, the current at the base side is 53.76 milliampere. Current at the collector is ICQ. Already it is 148 milliampere. 2 it is around 201.76 milliampere. This is IDC. Now what is the DC power? VCC into IDC. So total DC power is VCC 30 volts into IDC 0.20176 amperes. That is 6.05 watts. Now what is the output power? Output power we already know, 225 milliwatt. So you can see efficiency is 225 milliwatt divided by 6.05 watts. Total DC power by the circuit is 6.05 watts. AC power here is 225 milliwatts. 225 milliwatts is 0.225 watts. And the DC power is 6.05 watts. So the efficiency is only 3.72%. Yeah, the answers which students have given are not really very accurate, but I appreciate your efforts. I purposely wanted you to work out to some extent, but we will have to take care of all the intricacies here. What all we did not consider, we have to consider here. For example, the input power with respect to the input resistors also has to be considered. In the case of power gain calculation also, in the case of efficiency calculation also. That is why I wanted that you work out in your own way to some extent. Later on, let us see what is the accurate way of calculating. So this is how we calculate the efficiency. You can see the efficiency here is only 3.72%. That means the class A amplifier is not going to have larger efficiency at all. Now that is the problem with class A. As I have told you, we are working with the amplifier for the complete 360 cycle, and we want a faithful amplification there. In such a case, when we want to have a complete waveform of the input which is available at the output with a higher power, naturally we should compromise on the efficiency. So you can see the power gain is 1700 times. That is very good, but the efficiency is only 3.7%. That is very bad. But we have a compromise always in life as well as in technology also. We do not get everything everywhere every time. In some things we have to have a compromise. So when we have a power gain, we will have a reduction in efficiency. If at all you want to increase the efficiency or to save power, then you have to compromise on the power gain itself. That is how we design the amplifier circuits. Now this is one example which we have seen. I don't think I will be able to complete this slide today. Still I will show you. Class A amplifier with fixed bias. Whatever example we saw earlier was the class A amplifier with the voltage divider bias. Now let us analyze the circuit with the fixed bias, where we have a single resistor here, RB. Now naturally you know this will be VBE. If you apply KVL here, it is VCC minus VBE divided by RB is the current that is flowing. That itself is IB. We can easily calculate that. Other things are simple as we have seen it earlier in the very first module. Now here efficiency is again AC output power divided by DC input power. That is the DC power given to the circuit into 100%. Now this is the class A amplifier with fixed bias. Now let us see how to analyze. Maximum output voltage as far as AC is VCC by 2 root 2. That we have seen already, right? VCC by 2 root 2. The actual output is VCC now. Total output is VCC. When the transit is completely under cutoff, you can have VCC. You already know about the DC load line. So maximum output voltage is VCC divided by 2 root 2. That is V0 square divided by 8RL that way, right? As far as power is concerned. Now, as far as voltage is concerned, I have already shown you earlier. 0 to VCC is the value. If at all we have to take RMS value, then VCC by 2 is half. And you know that RMS is nothing but divided by root 2. One peak is VCC by 2. One peak divided by root 2 is VRMS. So we will have to always calculate power in RMS, voltage also in RMS now, because we are dealing with power amplifiers. So maximum V0 in terms of AC is VCC by 2 root 2. Maximum I0 AC is now VCC by 2 root 2 into RC, right? There is this RC here. So the maximum AC current is the maximum AC voltage divided by the resistor at the collector. So VCC by 2 root 2 into RC. So now maximum power for this circuit is what? Maximum power for this circuit, maximum P0 in terms of AC is VCC squared divided by 8RC. When you multiply this V0 AC into I0 AC, at the denominator you will get 2 root 2 into 2 root 2 as 8, and RC is there already at the denominator. VCC and VCC at the numerator get multiplied. So the maximum output power in case of this circuit without the load, please understand, we have not yet connected the load. If we connect the load, then we have to consider the load also in this calculation.